can't fall asleep. Your body is exhausted, but your mind refuses to be still. Thoughts drifting, looping, pulling you further away from rest. So tonight, don't try to silence them. Let's travel somewhere your thoughts naturally surrender, far beyond your room, beyond the noise, beyond the weight of the day, into the silent vastness of the Milky Way. A galaxy that appears calm from a distance, yet holds ancient collisions, vanished worlds, and echoes older than imagination. Breathe slowly. Release the day, and let your mind drift into the infinite. Picture our Milky Way galaxy as it exists today. A vast spiral of 200 billion stars, its disk stretching 100,000 light-years across, rotating in the cosmic dark like a slowly turning wheel of light. It seems permanent, eternal, unchanging. But look closer. Look at the halo of stars surrounding that disk. Look at certain globular clusters orbiting far from the galactic center. Look at stellar streams arcing across hundreds of thousands of light years, and you'll see the ghosts. 8 to 11 billion years ago, when the Milky Way was young, still forming, less than half its current size, something approached. A dwarf galaxy, slightly more massive than the small Magellanic Cloud we see in our southern skies today, was pulled inexorably by the Milky Way's gravitational embrace. This galaxy, which scientists now call Gaia Enceladus, or the Sausage Galaxy, contained approximately 500 million stars, vast clouds of gas and dust, and an invisible halo of dark matter, perhaps 10 times more massive than all its visible material combined. The collision, when it came, was catastrophic and slow. Gaia Enceladus approached not in a gentle orbital dance, but head-on, moving in retrograde, opposite to the Milky Way's rotation. Feel the scale of this encounter in your imagination. Two galaxies, each containing hundreds of millions of stars, approaching each other over millions of years, gravity pulling them together with a force more powerful than anything we experience on Earth. And then they met. Gaia Enceladus plunged through the Milky Way's disk like a stone through water. Its stars scattered, flung into chaotic orbits by the gravitational disruption. The gas it carried triggered violent bursts of star formation that lasted for 4 billion years. The impact puffed up the Milky Way's disk, creating what we now call the thick disk, a layer of older stars above and below the thinner disk where most star formation occurs today. All that remains of Gaia Enceladus now is debris. At least 8 globular clusters, dense spheres of ancient stars, were captured and still orbit the Milky Way. Blue stars in our halo, moving on highly elongated orbits with eccentricities near 0.9, are the scattered remnants of that dwarf galaxy's population. 50 billion solar masses, the combined weight of 50 billion suns worth of stars, gas, and dark matter were absorbed. Gaia Enceladus ceased to exist as a separate entity. It was consumed, digested, incorporated into the Milky Way's growing mass. But this wasn't the only meal. Earlier, perhaps 11 to 13 billion years ago, an even larger galaxy called Kraken contributed many of the Milky Way's 150 globular clusters. More recently, just 2.7 billion years ago, recent in cosmic terms, the Virgo radial merger brought another dwarf galaxy crashing through our galactic disk. And right now, as you lie here listening, the Sagittarius dwarf galaxy is being torn apart, its stars stripped away into immense tidal streams that wrap around the Milky Way like ribbons.
The Magellanic Clouds, those fuzzy patches visible in southern hemisphere skies, will someday share the same fate. The Milky Way is a cannibal. It grows by consuming its smaller neighbors, by pulling them in, tearing them apart, scattering their stars across the sky. The violence of this process is almost incomprehensible. Entire galaxies destroyed, billions of stars flung from their homes. And yet, paradoxically, it's also quiet, gentle, almost peaceful in its slowness. When we hear galaxy collision, we might imagine explosive chaos, stars smashing into each other, planets destroyed, civilizations wiped out in fiery cataclysm. But the reality is profoundly different. As Carme Gallart, an astrophysicist who studies these mergers, explains, it's not something like a car crash, it's something that has an effect on the galaxy as a whole. Picture two galaxies approaching each other. From a distance of millions of light years, gravity, weak, patient, inexorable, begins to pull them together. Slowly, over millions of years, they accelerate toward each other. And then they interpenetrate. One galaxy passes through the other, not colliding in any direct sense, but intermingling, their gravitational fields tugging on each other's stars. Here's what makes galactic collisions so strange, so unlike anything we experience in our daily lives. Stars are incredibly far apart. In our neighborhood of the Milky Way, the nearest star to our Sun is Proxima Centauri, over 4 light-years away. That's about 25 trillion miles of empty space. When two galaxies merge, when billions of stars from each system pass through each other, the chances of any two stars actually colliding is vanishingly small. The distances between stars are so vast that they simply slide past each other like ghosts, like mist through mist. Individual stars don't notice the merger in any immediate way. If you were living on a planet orbiting a star in Gaia Enceladus as it plunged through the Milky Way, you wouldn't feel an impact. You wouldn't see nearby stars exploding. What you would see, over millions of years, is your night sky slowly changing. The familiar constellations your ancestors knew would gradually shift, new stars appearing, old ones moving to different positions. Your star's orbit around the galactic center would change, becoming more elliptical, more chaotic. But these changes would be gradual, unfolding over timescales so long that thousands of generations might live and die before anyone noticed the difference. The astronomers studying these ancient mergers describe something they call wrinkles in stellar populations. When a dwarf galaxy collides with the Milky Way, it creates ripples, disturbances in the orbits and distributions of stars. These wrinkles persist for billions of years, slowly smoothing out over cosmic time. Thomas Donlan, who studies these patterns, poetically describes the Milky Way as a sort of cosmic Benjamin Button, getting less wrinkly over time, as these ancient disturbances gradually fade. The time scales are almost impossible for human minds to grasp. The Gaia Enceladus merger, began about 10 billion years ago. The collision itself, the initial penetration of one galaxy through the other, might have taken 100 million years. The subsequent absorption, the scattering of stars, the triggering of star formation, the gradual settling into current orbits, all of this unfolded over billions of years. 4 billion years of enhanced star formation. 6 billion years ago, the gas finally settled into the thin disk we see today, completing the transformation. And through all of this cosmic violence, silence. The vacuum of space carries no sound. No crash, no boom, no rumble. Just the silent pull of gravity, stars gliding past each other, separated by incomprehensible distances. Galaxies intermingling in a dance measured not in minutes or hours, but in millions and billions of years. The catastrophe is real, but it unfolds so slowly, so quietly, that it becomes almost peaceful. A meditation on the patience of the universe. Look up at the Milky Way on a clear, dark night, and you're seeing the combined light of billions of stars. But hidden within that river of light are the ghosts of the galaxies our home has consumed. Astronomers, using data from the Gaia spacecraft, which has mapped the positions and motions of over 1 billion stars, have learned to read these ghosts like archaeologists reading ancient texts. The most visible remnants are stellar streams, long, thin trails of stars stretching across vast distances of space. These streams are the tidal debris of consumed galaxies, stars pulled away from their parent galaxy by the Milky Way's gravity and strung out along their orbits like beads on a cosmic string. The Sagittarius stream, visible in our data, though not to the naked eye, wraps completely around the Milky Way, a ghostly ribbon marking the slow death of the Sagittarius dwarf galaxy. Globular clusters serve as another kind of fossil. These dense, spherical collections of stars, each containing hundreds of thousands to millions of stars packed into a relatively small volume, orbit the Milky Way like satellites. But many of them didn't form here. At least 8 globular clusters, including Messier 2, Messier 56, Messier 75, Messier 79, and others, were born in Gaia Enceladus and captured when that galaxy was consumed. They're immigrants, foreigners, carrying the chemical signatures of their birthplace. And those chemical signatures tell stories. Stars are made primarily of hydrogen and helium, but they also contain heavier elements, what astronomers call metals, like carbon, oxygen, iron. The specific mix of these elements depends on where and when a star formed. Stars born in the Milky Way have one chemical fingerprint. Stars born in Gaia Enceladus have another, subtly different. By analyzing starlight, breaking it into its component colors, and measuring the absorption lines that reveal chemical composition, astronomers can identify which stars were born here and which came from elsewhere. The halo of the Milky Way, that spherical cloud of thinly scattered stars surrounding our galaxy's disk, contains 2 distinct populations. Red stars that were always part of the Milky Way, flung into the halo by the gravitational disruption of the merger. And blue stars from Gaia Enceladus, the remnants of that consumed dwarf galaxy. Both populations are about 10 billion years old, identical in age, but different in origin. They're siblings and strangers at once, born around the same time in different places, now sharing the same cosmic home. About half the stars in the Milky Way's stellar halo, approximately 50%, descend from Gaia Enceladus. Half of what surrounds us came from elsewhere. We live in a galaxy built partly from immigrants, from the scattered remains of smaller systems pulled in by gravity and torn apart. And this means something profound. We are made from the dust of consumed galaxies. The heavier elements in your body, the calcium in your bones, the iron in your blood, the carbon that forms the basis of all organic molecules, were forged in stars. Some of those stars were born in the Milky Way, but others, statistically speaking, were born in galaxies that no longer exist, that were consumed billions of years ago, their stars scattered, their gas recycled into new generations of stars and planets, and, eventually, into us. In 4 to 4.5 billion years, the process will repeat. The Andromeda Galaxy, our nearest large neighbor, is approaching us at roughly 440,000 kilometers per hour. The distance between us is shrinking. In 4 billion years, give or take a few hundred million, Andromeda and the Milky Way will begin to merge. The collision will be spectacular, at least from a cosmic perspective. The two spiral galaxies will interpenetrate, their shapes warping and distorting. Star formation will explode as vast gas clouds collide and compress.
The night sky, for anyone still around to see it, will be dramatically different, filled with the light of Andromeda's stars growing ever closer. Over the next few billion years after first contact, the two galaxies will fall back together, merge again, gradually settling into a new configuration, probably an elliptical galaxy, bloated and featureless compared to our current elegant spiral. And through all of this, our solar system will likely survive. The chances of our sun colliding with another star are tiny, even in this cosmic catastrophe. We'll be flung into a different orbit perhaps, ejected from the galactic disk into the halo, or maybe just moved to a different radius. But we'll persist. The merger won't destroy us.
It will just give us a new home, a new context, a new galaxy to belong to. There's something comforting in this, a strange peace in understanding our cosmic origins and fate. We live in a galaxy that has consumed dozens, perhaps hundreds of smaller galaxies over its 13 billion year history. Our home was built from the dust and stars of others, and someday we'll merge with Andromeda, becoming part of something larger still. This is how galaxies grow. This is how structure forms in the universe. Through violence that's also creation, destruction that's also transformation, consumption that's also becoming. The Milky Way is a graveyard and a garden, both. The ghosts of consumed galaxies live on in our halo stars, in our globular clusters, in the very elements that make up our bodies. We are the children of cannibalism, born from the remnants of the devoured. And there's poetry in that, a reminder that nothing is permanent. Everything changes. All things eventually become part of something larger than themselves. Between one journey and the next, the universe never truly pauses. Stars continue their silent conversations. Light travels across impossible distances, and unseen worlds drift patiently along their paths. What feels like an ending is often just a change in perspective, a shift toward another story waiting to unfold somewhere among the countless lights of the galaxy. Tonight, we're going to journey to the loneliest places in the universe. Not distant galaxies or empty voids between galaxy clusters, but to worlds much closer than you might imagine. planets that drift through our own Milky Way in absolute darkness and profound solitude. These are the orphan worlds, rogue planets that belong to no sun, orbit no star, and wander through interstellar space with no destination, no purpose, no home. We'll explore their cold surfaces, their eternal night, and discover the strange, meditative beauty of existence without anchor. So settle deeper into your pillow. Let each word carry you outward into the dark, to places where time has no meaning and solitude is complete. There's nothing to do, nothing to remember. Just the gentle drift into darkness, into silence, into the peaceful surrender of belonging nowhere and everywhere at once. Imagine a world where the sun never rises, where there is no dawn, no dusk, no cycle of day and night, just eternal darkness, broken only by the faint pinprick glow of distant stars, so far away they provide no warmth, no light, no comfort. This is the reality for rogue planets, also called orphan worlds, nomad planets, or free-floating planets, celestial bodies that wander through space unattached to any star. These worlds were not always orphans. Most began their existence like Earth or Jupiter, forming in the swirling disk of gas and dust around a newborn star. But something went wrong. In the chaotic early years of planetary system formation, when multiple large planets jostle for stable orbits, gravitational interactions can become violent. One planet approaches another too closely. The gravity of both worlds tugs and pulls, and suddenly one is flung outward with such force that it escapes the star's gravity entirely. Picture that moment of exile. A planet, perhaps the size of Earth or larger, hurtling through space at thousands of miles per hour, watching its sun recede behind it. The light fades, degree by degree, hour by hour, until finally the star becomes just another point in the sky, indistinguishable from all the others. The warmth dissipates, the surface cools, and the planet begins its journey into eternal night, never to see daylight again. Not all rogue planets are exiles, though. Some are born orphans, forming alone in interstellar space from collapsing clouds of gas and dust, similar to how stars form, but without enough mass to ignite nuclear fusion. These planets never knew a parent star, never experienced the warmth of a sun, never orbited anything except the galaxy's distant center. They emerged into darkness and have known nothing else. How many of these lonely worlds exist? Astronomers studying the Milky Way estimate there could be billions, perhaps even trillions, of rogue planets drifting through our galaxy. They may outnumber stars themselves. In fact, in just one small region of sky in the constellation Sagittarius, astronomers discovered over 70 free-floating planets, and that was only a tiny glimpse. The true population is likely staggering. They're nearly impossible to see. Rogue planets emit no light of their own and reflect none from a nearby sun. They're dark, cold, and small by cosmic standards. To detect them, astronomers must use clever techniques, watching for the brief brightening of a background star when a rogue planet's gravity bends its light in a phenomenon called microlensing, or catching the faint infrared glow from young, still warm rogue planets using powerful space telescopes. These orphan worlds come in all sizes, from small rocky bodies not much larger than Earth to massive gas giants many times Jupiter's mass. Some may have once had moons,
companions pulled along during their violent ejection.
Others travel completely alone, singular points of mass drifting through an ocean of emptiness. To understand what it means to be a rogue planet, we must understand the sensory reality of their existence. Picture yourself standing on the surface of such a world. Not that you could actually stand there, the conditions would kill you instantly. But imagine it anyway. The darkness is absolute. There is no sun to rise in any direction, no star nearby to mark as yours. When you look up, you see what appears to be a night sky, but it's a night that never ends. The stars are there, millions of them, the combined light of the Milky Way creating a faint river across the black. But they're so distant that they provide no meaningful illumination. You could hold your hand directly in front of your face and see nothing. No shape, no shadow, no hint of form. Just darkness, pure and complete. The temperature is near absolute zero, around -270 degrees Celsius, -454 degrees Fahrenheit. At this temperature, any atmosphere the planet once possessed, if it had one, has long since frozen and fallen to the surface as solid ice. The gases that make up air on Earth would be hard as rock here. Nitrogen ice, oxygen ice, carbon dioxide frozen into dry ice, all of it coating the surface in layers of crystalline frost that have never melted and never will. The surface itself is alien beyond comprehension. If it's a rocky world, like Earth, the ground might be stone and metal, but covered in those layers of frozen atmosphere, creating a landscape of ice and frost that extends to every horizon. Hills and valleys, all frozen. Ancient impact craters, their edges sharp and perfect because there's no wind to erode them, no water to smooth them, no geological activity to reshape them. The surface is as it was the day the planet formed, or the day it was ejected, preserved forever in the cosmic deep freeze. If it's a gas giant like Jupiter, there might be no surface at all, just layers upon layers of hydrogen and helium clouds, swirling in patterns driven by internal heat from the planet's formation. These clouds would be dark, lit only by the faint glow of distant stars, moving in eternal storm systems that have raged for billions of years, with no sun to disrupt them. The silence is absolute. No atmosphere means no sound, no wind to whistle or howl, no waves to crash on any shore, because any oceans have been frozen solid, miles deep. No rain to fall, no thunder to rumble. If you could somehow stand on this world and shout, your voice would die the instant it left your lips, absorbed by the vacuum, traveling nowhere, heard by no one. And yet, paradoxically, these orphan worlds belong everywhere and nowhere at once. They're not bound to any particular region of space. They're citizens of the entire galaxy, free to wander wherever gravity's subtle currents take them. They pass through stellar neighborhoods without stopping, drift through the spiral arms of the Milky Way like leaves on a cosmic wind, cross from one side of the galaxy to the other over millions and billions of years. In their solitude, they possess a freedom that planets like Earth will never know. The most profound aspect of rogue planets is their complete lack of purpose or destination. When Earth orbits the Sun, there's a rhythm, a cycle, a return. 1 year brings you back to where you started. There's structure, pattern, predictability. But rogue planets have none of that. They drift. That's the only word that truly captures it. Not orbiting, not traveling toward anything, not escaping from anything. Just drifting through the galactic dark at whatever velocity their ejection or formation gave them. They move at thousands of miles per hour, incredible speed by human standards, but in the vast scale of the galaxy, they're barely moving at all. It might take millions of years to cross from one spiral arm to another, billions of years to complete a single orbit around the galactic center. There's something deeply meditative about this purposeless journey. No sunrise to mark the passing of days, no seasons to track the passage of time, no orbit to complete, no year to measure. Time becomes meaningless on a rogue planet. There are no cycles, no anniversaries, no return to familiar positions, just the eternal present stretching forward and backward infinitely, with no events to mark its passage. Picture the journey from the planet's perspective, if a planet could have perspective. You emerged into existence billions of years ago, either born alone from a gas cloud or flung violently from your birth system. Since then, you've been traveling through clouds of interstellar dust that dimmed the already faint stars, past other stellar systems, never close enough to be captured, always maintaining your independence, your solitude. You've witnessed stars be born and die, seen them flare and fade, all from your position of lonely observation. You have nowhere to be, no schedule to keep, no orbital dynamics to maintain. You simply are, existing in the dark, moving through space, not toward any goal, but simply because motion is your nature. You could continue this way forever. 10 billion, 20 billion, 100 billion years. And nothing fundamental would change. You would still be drifting, still alone, still moving through the same galactic dark. There's a strange peace in this, if you can find it. The peace of having no obligations, no expectations placed upon you. Earth must maintain its orbit or catastrophe follows. The moon must circle Earth or tides would cease and life would suffer. But a rogue planet? It can go anywhere, be anything, with no consequences. Its freedom is complete because it has nothing to lose, know where it's supposed to be, no role it's supposed to fulfill. In our connected, busy world, we fear solitude. We avoid it, fill every moment with sound and light and interaction. But the orphan worlds teach a different lesson, if we're willing to learn it. They show us that solitude, complete, absolute solitude, doesn't have to be suffering. It can be a form of existence as valid as any other. These planets have been alone for billions of years. There's no one to see them, no one to know they exist except for the rare astronomer who catches a glimpse through gravitational microlensing. They'll likely be alone for billions more. And yet, they endure. They persist. They continue their journey through the dark with a kind of quiet dignity, needing nothing from anyone, expecting nothing, simply existing. Some scientists speculate that certain rogue planets might even harbor life. If a planet has a thick hydrogen atmosphere, it could trap internal heat from radioactive decay in its core, maintaining temperatures warm enough for liquid water beneath kilometers of ice. Life could exist in those dark oceans, organisms that have never known sunlight, that evolved in and for eternal darkness, drawing energy from chemical reactions or the planet's own heat rather than from a star. What would such life be like? What would it think about, if it could think? Would it know loneliness, having never known company? Or would it simply accept darkness and cold as the natural state of existence, as unremarkable as daylight is to us?
Perhaps the greatest lesson of the orphan worlds is this:
belonging is not necessary for existence. Purpose is not required for meaning. These planets have neither home nor destination, neither past they're trying to return to, nor future they're working toward. And yet they are. They exist. They endure. They continue their silent journey through the cosmic dark with a completeness that needs nothing external to validate it. In a universe that often seems to demand connection, productivity, purpose, direction, the rogue planets offer a different model. The beauty of simply being, drifting through existence without need or want, complete in solitude, at peace in the dark. Time, in the vastness of space, moves differently than any traveler expects.
Moments stretch, civilizations rise and fade,
and distant echoes of events ripple across the cosmic ocean. As one narrative dissolves into stardust, another begins to take shape, carried forward by forces far older and greater than any single destiny.
Tonight's story unfolds over billions of years, yet feels as intimate as two dancers slowly approaching each other across a ballroom floor.
We're going to watch our home galaxy, the Milky Way, and our nearest major neighbor, the Andromeda Galaxy, engage in the longest embrace the universe knows. Not a collision, despite what the word suggests, not a violent crash, but a slow, patient merging. A meeting that takes longer than mountains take to rise and fall, longer than oceans take to form and evaporate, longer than species take to evolve and disappear. This is a story about inevitability, but gentle inevitability. About two vast communities of stars drawn together by gravity's patient hand. About homes that were once separate becoming one. About transformation so gradual that if you could witness it firsthand, you would see almost nothing change from one human lifetime to the next, yet everything change across the eons. So breathe deeply, let your eyes close or rest softly on the ceiling, and imagine looking up at a night sky not of today, but of tomorrow. Not tomorrow as in next week or next year, but tomorrow as in billions of years hence, when the heavens themselves will have been rewritten, and our galaxy will have found its cosmic companion at last. Right now, as you lie here, Andromeda is approaching us. It has been approaching for billions of years, and it will continue approaching for billions more. The galaxy moves through space at about 110 kilometers per second, which sounds fast until you remember the distances involved. At this speed, light itself would cross from Andromeda to the Milky Way in 2.5 million years. That's how far apart we are. 2.5 million light-years of void, sprinkled with a few small satellite galaxies stretching between our two homes. But space itself conspires to bring us together, not through any conscious intention, but through the simple mathematics of gravity. Each galaxy pulls on the other with invisible threads, threads woven from the curvature of space-time itself. The pull is gentle but inexorable, like water flowing downhill following the only path it can. If you could stand outside tonight and look up at the autumn sky in the northern hemisphere, you might see Andromeda with your naked eye. It appears as a faint smudge, larger than the full moon, but so dim that only dark, unpolluted skies reveal it. Most people live their entire lives without seeing it, lost as it is in the glow of streetlights in cities. But it's there, always there, a spiral of 1 trillion stars, twice as many as our own galaxy contains, suspended in the darkness like a distant lantern. The ancient light you would see left Andromeda 2.5 million years ago, when our human ancestors were just learning to walk upright across African savannas. The photons traveled through emptiness all that time, patient and unchanging, until they reached your eyes. By the time they arrived, they carried information about a galaxy that no longer exists in that exact configuration, because even galaxies shift and change, though slowly, so slowly. Now imagine time speeding up. Not in that frantic, accelerated way of time-lapse videos, but in a dreamy, unhurried flow. Years become seconds, centuries become heartbeats, millennia pass like breaths, and slowly, so slowly, Andromeda grows larger in the sky. 2 billion years from now, if anyone could still see it, Andromeda would appear noticeably bigger. Not dramatically so. You'd need to have perfect memory of what it looked like before, or perhaps a very old photograph to be certain. But it would be there, that subtle increase in size, that slight brightening, that gentle swelling in the autumn darkness. The approach is patient beyond human comprehension. Nothing in human experience happens on this time scale. Empires rise and fall in centuries, mountain ranges in millions of years. But this merging of galaxies takes billions. 4 billion years, perhaps 4.5, before the first close encounter. That's nearly as long as Earth has existed. It's longer than life has been multicellular. It's a span of time that makes all of human history look like a single frame in an endless film. And yet, for all that vastness of time, the galaxies draw closer. Inevitable as sunrise, certain as gravity. 2 spirals of light approaching each other through an ocean of darkness. Their mutual attraction written into the fabric of the universe itself. When we say the Milky Way and Andromeda will collide, we invoke an image of destruction, of violence, of things breaking. But galaxy mergers are not like car crashes or billiard balls striking. They are something else entirely. Something more like mist passing through mist. Ghosts walking through ghosts. 2 clouds interpenetrating without resistance. Consider the emptiness of a galaxy. Our Milky Way contains perhaps 300 billion stars, and Andromeda holds 1 trillion more. But even with all those stars, galaxies are mostly nothing, mostly void. The distances between stars are so vast that they dwarf the stars themselves by factors of millions. If you scaled the sun down to the size of a grain of sand, the nearest star would be another grain of sand 4 miles away. In between, nothing. Just emptiness. This is the typical spacing of stars in a galaxy. And when 2 galaxies merge, these enormous voids pass through each other almost entirely undisturbed. The chance of any 2 stars actually colliding during the Milky Way-Andromeda merger is essentially 0. You could run the merger simulation 1 billion times and might not see a single stellar collision. The stars are simply too small and too far apart. They're like snowflakes in separate storms, drifting through the same space at the same time without ever touching. But that doesn't mean nothing happens. Far from it. The stars may not collide, but they feel each other. Not through direct contact, but through gravity. As the two galaxies interpenetrate, every star in each galaxy tugs on every star in the other. The pulls are tiny, infinitesimal for any single pair of stars. But multiply that by hundreds of billions of interactions, and something extraordinary emerges. The galaxies begin to distort. Their elegant spiral structures, maintained over billions of years, start to warp and stretch. It's like watching two spinning records approach each other and begin to wobble and flex, their once perfect circles becoming ovals, then irregular shapes, then something that no longer resembles their original form at all. Streams of stars get pulled away from the main bodies of each galaxy, forming long tidal tails that stretch millions of light years into space. These are the debris of disruption, stars flung outward by gravitational forces, now traveling on new trajectories that will carry them far from their original homes. Some will eventually fall back. Others will escape entirely, becoming intergalactic wanderers, orphans, unattached to any galaxy. The dance unfolds in stages. First, approach, lasting millions of years, when the galaxies are still separate but beginning to feel each other's pull. Then the first close pass, about 4 billion years from now, when they swing by each other like partners in a waltz, close enough to be profoundly affected, but not yet merged. The spiral arms warp. Stars are redistributed. Both galaxies emerge from this encounter changed, their structures disrupted, their shapes no longer symmetric. Then they separate again, moving apart under their own momentum, but slowed by gravity. They pause, hanging at their furthest separation, before falling back together. This happens about 5 billion years from now, this second approach. And this time, they don't have enough speed to escape each other. This time, they merge. Over the next 1 billion or 2 billion years, the two galaxies blend together. Their stars intermix. Their gas clouds collide and compress. Their dark matter halos merge into one vast, shared gravitational well. And gradually, inexorably, what were once two separate spiral galaxies become a single elliptical galaxy. Smooth, rounded, no longer featuring the beautiful spiral arms that characterized both originals, but something new. Something that has never existed before in exactly this form. If you could somehow watch this merger from Earth, assuming Earth still existed and conditions allowed you to see the sky, the visual transformation would be among the most spectacular things the universe offers. Not sudden, but gradually accumulating into something magnificent. At first, as I mentioned, Andromeda would simply grow larger over millions and billions of years. That faint smudge in autumn skies would brighten and expand, claiming more and more of the celestial sphere. By the time of the first close approach, around 3.75 billion years from now, Andromeda would dominate the night sky. Its spiral arms would stretch across huge swaths of darkness, no longer requiring a telescope or even particularly dark skies to see. It would be obvious, undeniable, magnificent. The light from Andromeda, and from our own Milky Way seen from a different angle, would stretch across the void between galaxies in visible threads, not in the sense of light beams like flashlights, but in the sense that the stars themselves, flung into tidal tails during the gravitational interaction, would trace luminous arcs through space, bridges of light connecting the two galaxies, streamers of stars pulled loose and scattered like seeds on stellar winds. During the closest approaches, bursts of new star formation would ignite. When galaxies interact, their gas clouds collide in ways individual stars do not. Gas, unlike stars, does collide. It compresses. It heats. And when it heats sufficiently, it triggers the collapse that births new stars. Thousands of them. Millions. All at once. In what astronomers call starburst regions. These newborn stars would burn hot and blue, massive and bright, flooding their surroundings with intense radiation. The night sky, for any observer positioned correctly, would blaze with light. Not the familiar scattered points of individual stars, but entire nebulae glowing with the luminescence of stellar nurseries. Clouds of ionized gas lit from within by infant suns, painting the darkness in shades of red and pink and blue. The visual chaos would be unlike anything visible from Earth today. Our current night sky shows the Milky Way as a band of light arcing overhead, a river of distant stars too faint to resolve individually. But during the merger, you wouldn't see one band, you'd see two, intersecting, warping, stretching. The Milky Way twisted into unrecognizable shapes, Andromeda pulling it into new configurations. Both galaxies losing their identity as distinct objects and becoming something in between, something transitional, something that is neither one nor the other, but both and more. By about 5 billion years in, during the second close pass, the cores of both galaxies would appear as dual bright points in the sky, two centers of mass, two concentrations of billions of stars, orbiting each other like binary stars, but on a scale millions of times larger. They would spiral inward, drawn by dynamical friction, the process by which moving massive objects transfer their orbital energy to the stars around them, gradually slowing and falling toward the center. And the light would be extraordinary, not just from stars, but from the supermassive black holes at the center of each galaxy. As gas falls toward these black holes during the merger, it forms accretion disks, super-hot whirlpools of matter spiraling inward. These disks can outshine entire galaxies, releasing as much energy as 100 million supernovae. For a time, perhaps a few million years, the center of the merged galaxy might become a quasar, a brilliant beacon visible across the universe, fueled by matter plunging into the combined black hole. From any vantage point within the merging system, the sky would be unrecognizable compared to today. No familiar constellations, no Milky Way band in its accustomed place. Just a new sky, bright with young stars, threaded with tidal streams, centered on a blaze of light from the galactic core. It would be terrifying and beautiful, chaotic and magnificent, unlike anything anyone has ever seen. Eventually, the chaos settles, not quickly. Nothing about galaxy mergers is quick, but eventually. About 7 billion years from now, maybe a bit more, the merger would be complete. The two supermassive black holes would have spiraled together and merged into one, releasing a final burst of gravitational waves that would ripple through space-time itself. The two cores would have blended. The stars from both galaxies would be thoroughly mixed, their orbits randomized, no longer arranged in the orderly spiral patterns that characterized their origins. What remains is Milky, the informal name astronomers have given to this future merged galaxy. Not a spiral anymore. The merger process disrupts spiral structure, consuming the gas that makes spiral arms visible, redistributing the stars into more random orbits. What emerges instead is most likely an elliptical galaxy, smooth and rounded, shaped more like a football than a disk.
Elliptical galaxies are the retirement homes of the cosmic world.
They contain mostly old stars, having used up most of their gas in earlier rounds of star formation. They're more stable than spirals, less dynamic, less active. But they're also vast and luminous, containing the combined light of trillions of suns. For any civilization that might exist in Milky, the sky would be different than ours in fundamental ways. No more Milky Way band arcing overhead. Instead, the entire sky would be more uniformly populated with stars, though perhaps less densely than the Milky Way's disk appears to us. The night would never be truly dark in Milky, not if you were near the galactic center, where stars pack more closely together. But there would be a profound calm to it.
The turbulence of the merger would be over.
The starburst regions would have faded as their massive blue stars burned out. The tidal tails would have either fallen back into the main body of the galaxy or dispersed entirely. What would remain is a new equilibrium, a new stable configuration, a galaxy that has found its final form. This is the way galaxies grow, not through slow accumulation of individual stars, but through mergers. The universe is full of elliptical galaxies, most of them likely formed through mergers of spirals in the distant past. Our Milky Way itself has consumed dozens of smaller galaxies over its history, and Andromeda has done the same.
This upcoming merger is just the next step in a process that has been ongoing since the first galaxies formed over 13 billion years ago. There's something peaceful in this, if you think about it in the right way. Not the specifics of the process, which involves tremendous energies and transformations, but the overall arc. Two separate things becoming one. Two homes becoming a single, larger home. Stars that were once neighbors only to Milky Way stars, becoming neighbors to Andromeda stars. A mixing, a blending, an enlargement of community. The stars that originated in our galaxy and the stars that originated in Andromeda will be indistinguishable after the merger. You won't be able to look at a star and say, that one came from the Milky Way, or that one came from Andromeda. They'll just be stars in Milky, part of the new whole, their origins erased by time and mixing. And perhaps there's a metaphor there for sleep itself. When you sleep, the boundaries of self become less distinct. Your consciousness, which during waking feels so separate and defined, disperses into something more diffuse. You are still you, but the borders soften. Past and present blend. Memories and imagination intermix. What was once held separate comes together in dreams.
The galaxies sleep into each other over billions of years, their separate identities gradually dissolving into a shared identity, until what emerges is neither one nor the other, but both. A new entity that contains all that came before but arranged in new patterns. A new configuration, a new home in the cosmic sea. No path through the galaxy is ever truly isolated. Every choice, discovery, and encounter becomes part of a larger tapestry woven across the Milky Way. While one chapter closes in the quiet glow of fading stars, another awakens beyond the horizon of the unknown, where new mysteries, dangers, and wonders patiently await.
We're going to rest at the edge of a black hole. Not the terrifying monster of science fiction, but the quiet heart of our cosmic home. The point of absolute stillness around which 400 billion stars revolve in their slow, patient orbits. As you settle into sleep, imagine yourself not falling, but floating. Not lost, but found. Because at the center of our galaxy, in the presence of Sagittarius A star, we discover something unexpected. Peace in paradox, calm in contradiction, and rest at the very edge of the unknown. Sagittarius A star sits like a pearl in the center of our galaxy. But this pearl weighs 4 million times more than our Sun, compressed into a space smaller than the orbit of Mercury. To call it massive seems almost inadequate. To call it dense misses the point entirely. It exists beyond the language we have for describing things, in a realm where words begin to fail and mathematics takes over. The name itself carries a strange poetry. Sagittarius, for the constellation where it appears to rest from our perspective here on Earth. The asterisk, added by astronomers to distinguish it from the larger radio source surrounding it, a typographical mark that somehow fits this cosmic punctuation, this period at the end of a sentence written in starlight and gravity. For most of human history, this object was invisible to us. Not because of distance alone, but because 25 magnitudes of dust and gas stand between Earth and the galactic center, absorbing and scattering light like fog obscuring a distant lighthouse. We couldn't see it in optical wavelengths, couldn't photograph it with normal telescopes, couldn't prove it existed at all until we learned to look in radio waves and infrared, peering through the cosmic haze to find the dense, bright, compact source that had always been there, patient and eternal. And here lies the first paradox. This object, this concentration of such immense gravity that even light cannot escape its grasp, is the very thing that makes our galaxy possible. Without it, the Milky Way would not hold its spiral shape. The hundreds of billions of stars that make up our galactic home would drift apart over cosmic time, unbound, scattered like seeds on stellar winds. The black hole doesn't control the motion of distant stars directly. Its gravity, though profound, extends in meaningful ways only to the nearest stars, those within a few light years of the center. But it represents the densest point in the gravitational field that shapes our entire galaxy. It is both the destroyer and the anchor, the void and the foundation. Think of it this way. A black hole is not a cosmic vacuum cleaner, not a hungry mouth constantly feeding. Sagittarius A star is, by the standards of supermassive black holes, remarkably quiet. It feeds slowly, consuming perhaps a 10/1000th of a solar mass each year. That's less than the mass of the dwarf planet Ceres annually, a trickle rather than a flood. The last time it had a truly substantial meal was somewhere between 5 million and 9 million years ago, when it swallowed perhaps 100 times the mass of our Sun
in what must have been a spectacular outburst. Most of the time, it simply exists, a point of absolute stillness, the calmest place in the most turbulent neighborhood of our galaxy. Stars whirl around it at tremendous speeds, some completing orbits in just 16 years, traveling at several percent of the speed of light. But the black hole itself does not move, does not flee, does not change. It is the definition of permanence in a universe of constant motion. This is the paradox that lets you rest tonight. The most destructive force we know is also the source of cosmic stability. The thing that devours light makes brightness possible. The ultimate darkness sits at the heart of our luminous spiral home. You cannot see the black hole itself. This much is certain. The event horizon, that boundary beyond which nothing returns, emits no light of its own. It is a shadow, a silhouette, an absence cut into the fabric of visible reality. But around it, around it, there is splendor. Imagine a disk of matter, gas and dust captured by gravity, spiraling slowly inward like water circling a drain. But this is no ordinary disk. This is an accretion disk, and it glows. Not with reflected light, but with its own fierce radiance, generated by friction and compression, and the inexorable pull of gravity transforming motion into heat. The disk around Sagittarius A star is relatively small, only a few times the diameter of our solar system. But within that space, temperatures range from bitter cold at the outer edges to tens of millions of degrees near the center. The hottest regions emit X-rays, invisible to human eyes, but detectable by our instruments, speaking to us across the vast distance in the language of high-energy photons. But if you could somehow see it with different eyes sensitive to all wavelengths at once, you would witness a riot of color. The outer disk might glow deep red, cherry red, the color of cooling metal still holding warmth. Moving inward, the colors would shift through orange and yellow as temperatures climbed. Closer still, the light would become white-hot, then blue, then a brilliant blue-white that exists nowhere on Earth except in the hearts of arc welders and lightning strikes. The disk is not uniform. It roils with turbulence, with magnetic fields that twist and tangle through the superheated plasma. Bright knots form and dissipate, regions where material clumps together briefly before being sheared apart by differential rotation. The inner edge spins at a significant fraction of light speed, while the outer portions move more sedately. And this difference in velocity creates stress, friction, heat, and light. There is something else happening here, too. Something subtle, but profound. The light from the side of the disk moving toward us appears brighter and bluer than it should, while the light from the receding side appears dimmer and redder. This is the Doppler effect, the same phenomenon that makes an approaching ambulance siren sound higher-pitched than a departing one, but taken to relativistic extremes. Material in the disk moves so fast that it compresses and stretches the wavelength of light itself, and gravity bends the light's path. Photons leaving the far side of the accretion disk don't travel in straight lines, but curve around the black hole's mass, bringing us images of regions we shouldn't be able to see. The disk appears to wrap above and below the black hole's shadow simultaneously, defying our usual understanding of perspective and geometry. If you could float there, somehow protected from the radiation and heat, you would see light doing impossible things. You would see the entire universe compressed into a bright ring behind you, an Einstein ring where space-time's curvature focuses distant stars into a perfect circle. You would see parts of the accretion disk that lie behind the black hole appearing to float above and below it, their light guided around the event horizon by gravity's patient hand. The colors themselves would seem alive, pulsing, shifting with the turbulent flow of matter through magnetic fields strong enough to tear atoms apart. The brightness would flicker on timescales of minutes and hours, as clumps of material make their final approaches to the event horizon, releasing their last energy before crossing the boundary into silence. This vortex of light, this luminous maelstrom, surrounds a darkness so complete that it has become a thing unto itself. The shadow cast by the event horizon appears larger than the horizon itself, a consequence of light bending that makes even this absence seem more substantial than it should. Inside that shadow, there is nothing for us to see or know or understand. Just the perfect calm of the unknowable. Now we come to perhaps the strangest aspect of our cosmic anchor. Time itself behaves differently here. Near the event horizon of Sagittarius A star, the river of moments flows at a different pace than it does on Earth, or even at the outer edges of our galaxy. This is not metaphor or poetry. This is measured, verified, mathematical reality. Time dilation, they call it. The stretching of time. It emerges from Einstein's recognition that space and time are not separate things, but woven together into a single fabric that gravity warps and bends. Mass tells space-time how to curve. Space-time tells mass how to move. And in the presence of something as massive as a supermassive black hole, the curvature becomes extreme. Imagine you could observe someone falling toward the event horizon. At first, you would see them accelerating, gaining speed as gravity pulls them inward. But as they approach that boundary, something strange would happen. They would appear to slow down. Their movements would become more and more sluggish. A wave of their hand that should take a second would seem to take a minute, then an hour, then longer still. The light coming from them would redshift, stretched toward longer wavelengths by the extreme gravitational field, changing from white to red to infrared to radio waves, growing dimmer and dimmer, not because they're moving away, but because photons themselves are losing energy, climbing out of the gravitational well. Eventually, they would seem to freeze completely, suspended just above the event horizon for all eternity, growing darker and darker until they faded from view entirely. But this is only what you would see from a distance. For the falling person themselves, the experience would be entirely different. They would not feel time slowing. Their watch would tick normally. Their heart would beat its usual rhythm. They would cross the event horizon in a finite amount of time, probably quite quickly, and never perceive any moment of slowing or stopping. This is the profound strangeness of relativity. Time is not universal. There is no single clock ticking away the moments for the entire universe. Instead, time is local, personal, dependent on your motion and your position in the gravitational field. A clock at sea level on Earth runs slightly slower than a clock on a mountaintop. The difference is minuscule, measured in nanoseconds over a lifetime, but it exists and can be measured. Near Sagittarius A star, these effects become dramatic. Spend a year orbiting close to the event horizon, and when you returned to Earth, decades or even centuries might have passed here. The time dilation factor grows stronger and stronger as you approach the boundary, until at the event horizon itself, from an outside perspective, time appears to stop completely. This creates a curious philosophical situation. From outside, nothing ever quite crosses the event horizon. Everything approaching it seems to slow to a frozen halt, suspended there eternally. The black hole is surrounded by a shell of apparently motionless matter, growing dimmer and dimmer, but never quite disappearing, never quite falling in. Yet we know from mathematics that matter does cross the horizon, does continue inward, does reach the singularity at the center. The paradox resolves only when we recognize that there are two valid descriptions of reality here, both true, neither contradicting the other despite seeming to do so. The person falling in experiences one timeline. The distant observer experiences another. Both are correct, both are real. As you rest here tonight, at the edge of sleep, perhaps you can appreciate this strange comfort. Time itself is gentler than we thought, more flexible, more forgiving. The universe makes room for different experiences of duration, different paces of existence. Near the heart of our galaxy, time stretches and slows. And in that slowing, there is a kind of peace. There is something deeply calming about the event horizon once you understand what it represents. It is a boundary, yes, but not a wall or barrier in the usual sense. It is simply the place where the escape velocity equals the speed of light. Cross it, and you cannot return. Not because something blocks you, but because the geometry of space-time itself curves back on itself so profoundly that all paths lead inward. From inside, looking out, you wouldn't see anything special about the moment you crossed. Space would still look like space. The stars behind you would still shine, though their light would be blue-shifted to higher energies by your motion and the gravitational field. Time would still feel normal, your thoughts still coherent, your consciousness still intact. At least until tidal forces began to stretch you in ways that biology cannot withstand. But from outside, you would have vanished at the threshold, or seemed to, fading away asymptotically toward an eternal pause. Your information, your pattern, the specific arrangement of matter and energy that comprises you, would still be imprinted somehow on the event horizon itself, encoded in quantum fluctuations that persist there, or so some theories suggest. The information paradox remains unresolved, one of the deepest puzzles in modern physics. This is the ultimate unknown. What lies beyond the event horizon, at the singularity where density becomes infinite and our equations break down? We can make educated guesses. We can extend our mathematics as far as it will go. But ultimately, we cannot know, cannot see, cannot verify. The event horizon is the boundary between physics and metaphysics, between the knowable and the unknowable. And there is profound peace in that. Our lives are filled with anxiety about the future, with desperate grasping after certainty. We want to know what will happen, how things will turn out, whether our plans will succeed. We crave control and predictability. But the event horizon reminds us that the universe contains genuinely unknowable things, places our knowledge cannot reach, questions our science cannot answer. And this is okay. This is simply how reality is. Sagittarius A star has existed at the center of our galaxy for billions of years. It was there before the Sun formed, before Earth coalesced from the protoplanetary disk, before any life stirred in any ocean anywhere. It will likely still be there long after our Sun has burned out and died, after Earth is cold and lifeless, after everything we know has returned to dust and gas. It is patient beyond human comprehension, eternal by any standard we might apply. And it is mostly at rest, not moving through the galaxy, not consuming voraciously, not doing much of anything, really. Just being, just existing as a point of perfect stillness while the galaxy turns around it in its slow cosmic dance. 400 billion stars pursuing their orbits, new ones being born, old ones dying, matter cycling through the spiral arms in an endless process of death and renewal. And at the center of it all, calm, permanence, the anchor that holds it all together. As sleep takes you tonight, imagine yourself floating there at the edge of the event horizon, not falling in, just resting, held in place by some impossible technology, protected from the radiation and tidal forces, existing in that strange space where time moves differently. Behind you, the entire universe appears compressed into a bright ring. Before you, the perfect darkness of the event horizon, smooth and featureless, offering no information, no answers, no certainty. And in that absence, in that void, in that unknown, you find something unexpected. Not terror, but tranquility. Because you don't need to know what lies beyond. You don't need to understand everything. You don't need to solve every mystery. Some things can remain unknown. Some boundaries can remain uncrossed, and that's okay. The heart of the spiral turns in darkness. Time stretches thin like honey poured in winter. Light bends and dances around the shadow. And you, here on your pillow, 26,000 light years away, can rest in the knowledge that somewhere, at the center of everything, there is stillness. There is calm. There is peace at the edge of the unknown. If you enjoyed this journey to the heart of our galaxy, please consider liking this video and subscribing to Pillow Trace for more interesting stories to listen to before bedtime. Sleep well, and may your dreams carry you safely through all the unknowns that wait beyond the edge of waking.